So hello everyone. This is our tutorial number 1 for the course NPTEL course Concepts in Magnetism and Superconductivity. Uh, so as you know, this is the first tutorial of this course, and in this course, so basically we have already you have already probably given access to all the week 1 lectures, and this week's tutorial is probably mainly based on the topics that you have covered in the week 1 lecture of the course. So basically, I'll tell you what this tutorial will be about. So basically, you will be taught about some concepts and topics in the main week lectures, and then if you you will be given some assignments to solve, and you have to submit them by the deadline mentioned in the website, and you have to solve them and submit them. So basically, those assignments will be related to whatever things you are taught in the week lectures, and if you have some doubt in the assignments, you can ask for hints in the tutorial sessions, but I will not solve the assignments for you before the deadline, because in that case it will, because those are graded assignments, right? So at maximum I can give you some hints of how to solve. If any of you face any problem in any of the solution, you can ask me directly in the tutorial. Apart from that, what we will do is that we will mainly focus on solving more and more similar type of problems in the tutorial session. So basically, like say in this session, one second, yeah. So in this session, I will not solve the actual week 1 assignment that you are given to solve for this week, and the deadline is 8th August. Remember to solve and submit the assignment before that. But in this tutorial, I will mainly go through some similar type of problems which are mostly based on the same topics that you are already familiar with if you have already watched the week 1 lectures, and if you still have not, then please watch that, and then we can always discuss if you have some doubt. So then let us try to solve. First look at the questions, and we'll try to solve them one by one. So here we'll have 10 questions. So we have 10 questions which are related to topics of week 1 lecture content. So I hope I am properly visible and also audible, and the screen is probably visible to you. Okay, so if at any point if you have some doubt, you can always stop and ask me right there. Okay, so then let us start with question 1. So question 1 is basically not a mathematical problem, it is a conceptual question. Let us read that question first. So question 1 says that what is a fundamental object in magnetism? So this is the most fundamental question of this course, right? Because this course is concepts in magnetism and superconductivity. So this is mentioned in the very first lecture itself of week 1. The right answer will be option number 2, which is magnetic moment. Now you can see the other options are like magnetic field, bar magnet, lodestone. So these are bar magnet, lodestone, these are some magnetic objects. So these are not some fundamental thing that we can talk about. Other than that, magnetic field is not some fundamental object in magnetism, because first you have to understand that why magnetic moment is the most fundamental thing. So it is the most basic concept of the course, right? So I'll elaborate on it a bit. You may know it already, but I like to elaborate on it a bit. So what is magnetic moment? Magnetic moment is basically, you can say it is like an atomic scale origin of the this magnetic moment has some atomic scale origin. I mean, in a material you have it consists of many atoms, right? So every atom individually can have a magnetic moment, and that is what defines a magnetism in the whole material. When we consider magnetism in a solid, basically we have to consider the individual magnetic moments coming from each of the atoms. So that takes us to the origin of magnetism, because let's say if you have a solid object like this, so this is, let's say, a solid object, and it has some magnetic properties, let's say. So this is, let's say, magnetic. Now, what is a solid basically? So solid is consisting of many atoms, right? So like if it is a solid material, so in the atomic scale you can see there will be many atoms that the solid is made of. So like say these circles I am drawing inside, let's assume that these are some atoms which are combinedly making up the whole solid object. So these are atoms that the solid is made of. Okay, so now each atom has an individual magnetic moment. Each atom has an individual magnetic moment. Alright, so yeah, so if that is the case, then you can so let me go to a blank page so that I can write in details. So this is the explanation for question number 1. So what this atomic magnetic moment, the atomic origin of magnetic moment looks like. Origin of magnetic moment. Okay, so you can assume that there is this current loop. Okay, so this is the current loop on which there is a current I that is flowing in a particular direction that is marked by this arrow. Now you can think of the infinitesimal magnetic moment element, which is d mu, that is defined as I times ds. Now I is the current that is flowing through the whole loop, and what is ds? Ds is basically an infinitesimal area of the loop. Infinitesimal area of the loop. How to define that? Let us draw something. So we can always divide the whole loop into many small infinitesimal parts like this. So like say if you try to blockwise divide it, so in my drawing they may not look uniform, but you can assume that these are uniform blocks that I have been drawing by these lines inside the loop. So similarly, this kind of a single block, if you choose, so this is basically a single element inside the loop, infinitesimal area element, you can say. This is what I am blocking with white color here. So this is one single loop part, right? So this is kind of like an infinitesimal loop, or a like elemental version of the loop. So this loop will also have a similar current boundary around it, and this has an area with the area element vector that is perpendicular to the loop in this direction, arrow direction, and it has some current also effectively coming from the loop current I. So what will be the magnetic moment that is associated to this portion, this infinitesimal portion of the current loop? So that is defined as d mu, which is nothing but current times the area. So this is a generic definition of magnetic moment that you have to remember, that always when you have some magnetism, so it is basically related to some current flow, right? So in electric field or in electric field, you know that when there is a charge, it creates a magnetic field, and that charge is a static electric charge, right? So like if there is a positive charge of plus q, it is a static charge, that means it is not moving, so it will give rise to a electric field around it, that is given by E vector. Similarly, in magnetic field or in magnetism, you can question that how does it appear, but this is the convention, or this is a well-known notion, that magnetic monopoles do not exist. So you cannot define a magnetic monopole like this charge can be thought of a electric monopole, right? But in magnetism there is no thing such as magnetic monopole. So all you have is that starts with magnetic dipole, and that is basically nothing but a current loop. So whenever you have a current flowing in a particular direction, as per that direction there is a magnetic field that is produced. So like here, if you see that this is a anti-clockwise directional current loop, okay, anti-clockwise direction arrows are given, and then it will create a magnetic field in the upward direction. So this is the basic convention. You can check it from the right hand thumb rule. Also, if you have a current loop with a, let's say, clockwise current direction in the loop, then the magnetic field effectively produced by that will be in the downward direction. So this is the basic convention of how a current loop creates or generates a magnetic field. Now this is about the magnetic field, but in the same manner, if there is a magnetic field, so if, let's say, if there is some object also that is put inside that loop, so what will happen when you flow a current on that loop is that it magnetizes the object inside. So basically it produces some magnetic moment in the atoms that the solid object is consisted of. Okay, so, and the most fundamental concept about magnetism is basically magnetic moment. So this is the infinitesimal portion of the magnetic moment d mu that is coming from the contribution of this small infinitesimal loop portion inside this whole total loop, and this is defined as current times area. So this is the generic definition that magnetic moment, this is a very important formula, that magnetic moment is basically the current in the loop into the area element. If it is an elemental area, then the area element ds, or if it is a whole area, then the total area will be considered. And now for the total loop, if you have to consider the moment, so the total magnetic moment of the current loop is basically nothing but the integration over all such small parts, right? Because there are many number of such small portions that we can again and again hash and show like these parts. So you have to you need a total sum over, right? So you have to do a integral over the infinitesimal magnetic moments. So the mu total is basically mu equal to integration over all the small or infinitesimal magnetic moments coming from the individual area elements. And because the constant current is the same current that is passing through the boundary of the loop, because if you go and check, then you will see that all the inside portions of this loop, there will be current that will be cancelling out each other, only leaving the current on the external boundary. What I mean is that basically, say, let me again draw it. Let's say for your convenience, I am drawing a large size element box. So this is just for your convenience. It should not be such large size, otherwise it will not be an elemental space. So let's say this is the external loop current I that is flowing through the loop boundary in this direction. Now let us consider let's say this element box inside the loop area. So let's say this blue colored one. Okay. So now if you try to draw what is the current direction on this particular small loop boundary, what will be that? So basically you have to like maintain the same current direction. So it will be like here, this will be in this direction, and then this direction, then like this and like this. So this is the internal loop current, if you want to assume like this will be the case. Now let us consider another infinitesimal area of the loop just right beside the earlier one, which we now cover it with a white shade, so that you can identify the first one is in the blue shade and the second one is in the white shade. Now if you again try to find out what is the current direction, what will be the current direction in the internal portion of this infinitesimal area, then following the same current direction again, here this will be this direction, then this direction, then it will be like this, and then it will be like this downwards. So now just take a look that these two boxes, this blue box and white box, they are side by side with each other, right? And if you just take a look at this current loop on the right of the blue box, which is in the upward direction, and on the left of the white box, which is in the downward direction. So this two loop elements which are right beside each other have a current arm which are exactly equal and opposite for the two areas. So for the blue area, it is in the upward direction, and for the white area, it is in the downward direction. So what will happen is that basically these two will cancel out each other as they are side by side and they are equal and opposite direction. Similarly, no matter how many boxes you choose from the whole elemental area, whatever elements, how many elements you can draw, as many as elements you can draw inside the loop, you will get to see the same thing happening again and again, that all the boxes adjacent to each other, all the loop elements will have some current element which will be equal and opposite to the other current element right beside that, and they will cancel out each other. Only at the end, when you finish up all the loops, you will see that all the internal currents will be cancelled out. Like here, this direction will be this loops, this direction current will be in the upward direction, so they will also cancel out each other. Okay, so let me choose a red color here. So they will also cancel out each other, and similarly everything will be cancelled out except for this external loop current that you initially started with. That will be the only thing that will survive through all the loop cancellation and everything, and it will flow across the external boundary of the loop. So this is the current that is surviving, and this current is I. So that is why for any loop element, even if the elemental loop is different, but the current I is effectively same for all. So when you take an integral of the individual magnetic moments of each element d mu, you have to take an integral over the whole thing. So the I is constant, so it comes outside the integral, and you are left with ds, the area element, integrated for all the small areas, and as a result you will get the total area. Let's define as A. So your entire total magnetic moment of the loop is the loop current I that is flowing through the loop boundary, and the total area of the loop, that means total area A is what? This is the total area that is covered or that is bounded inside this whole boundary of the loop. So this is the area A. This area is basically sum over all the individual loop elements that are present inside the loop, and there you have the definition of magnetic moment as the current inside a loop and multiplied by the area of the loop. So this is basically the fundamental idea of magnetism, that it starts always with a magnetic moment, and magnetic moment has an atomic origin in the sense that whenever you have a solid, if you have some many number of atoms that the solid is consisted of, and those each of those atoms has a magnetic moment corresponded to it. Okay, so that is why this gives you the answer to your first question, that the most fundamental object in magnetism is nothing but the magnetic moment. Okay, done. Then our first question is done. So this is basically just a conceptual question. Similarly, the second one, if you follow, it is also again a conceptual question. Let us read that out. So question number 2 says that the magnetic moment mu is related to the angular momentum omega, or sigma, whatever you can call it. So this angular momentum omega, as there are 4 options given, where this is first option is that they are inversely proportional to each other. Second option is that mu is proportional to square root of omega, the angular momentum. Third option is that mu is directly proportional to the angular momentum omega, and fourth is that mu is not related to angular momentum at all. So if you have properly followed the weekly lectures, then you already know the answer. I don't have to give you the answer, you already probably know it. But for those who have not really followed, and this is very easy to make a mistake here, because apparently you will think that what will be the connection between a magnetic moment which has a magnetic property with the angular momentum, right? Because those two are completely different things. Magnetic moment is somewhat corresponded to some current flow or some, like, some current loop, some moment, etc., right? But angular momentum is something that, like, say, linear momentum comes as a product of mass times velocity, right? The linear momentum p is basically mass times velocity. But angular momentum, this is nothing but r cross p. If r is the position vector and p is the linear momentum vector, so it is basically a cross product of that, and it is also nothing but it is related to some angular velocity of the material, if you can define that. So basically it is something that actually is related to the mass of the material, or the positional, this r vector cross p vector. That means it is basically, if you ignore the vector direction and etc., if you just consider the magnitude, you will see that this is nothing but mvr, where m is the mass of the object, v is the velocity of the object, and r is the distance or position, whatever you can define, of the object from some reference point. So basically your angular momentum is something that is corresponded to the mass and the mass of the element as at least, whereas your magnetic moment mu was something like current flowing through a loop into the loop area, right? So current means it is charge by time, some charge by time, q by t, let's say, into area. So here it is directly related to some electric property, which is the charge, and the angular momentum is related to some mass property, which is the mass of the material. So how can these two both be related? So you can some of you can naturally do the mistake and choose option number 4 as the option, but this is totally not the right option. The right option will be option number 3, where it says that the magnetic moment mu will be directly proportional to the angular momentum omega. And why will that be the case? Let us check. Let me take a blank portion of the page. So question number 2. Now the concept is that your magnetic moment is directly proportional to the angular momentum omega. And if you can define a proportionality constant, then it is mu equal to gamma times omega. So this is a very fundamental relation in magnetism that you have to remember always, that the magnetic moment and angular momentum are related by this proportionality constant gamma, which has a special name that it is called the gyromagnetic ratio. Gyromagnetic ratio. And there is a proper calculation which shows that gyromagnetic ratio is nothing but the value is E by twice m, or twice me you can say, where me is nothing but the electron's mass, E is the electronic charge, and gamma is the gyromagnetic ratio. Now the question comes that how they are two both related, right? So now the connection, making the connection is all dependent on the fundamental basics of the topic. What is that? So let us think of it this way. Let us take a very simplified picture. Let us take the idea of, let's say, hydrogen atom. Okay, hydrogen atom means you have a single electron and a single proton, right? So this is your nucleus of the hydrogen atom, this blue circle inside. So this is a single proton, so a single plus charge and no neutron. So if you have protein, right, so each one single proton and single electron, no neutron. So you have a plus charge in the nucleus inside, and similarly on the external orbit you have a single electron present. So this is the electron. It has a negative charge, so this is minus E. Now this electron is moving in a circular orbit. You know that this is the atomic structure, that if in an atom you have a nucleus which is positively charged because protons are there, and then even if neutrons are there, you know that neutrons are neutral, they do not have any electric charge. So that's why I am saying that inside you have a nucleus of positive charge, and on the outer orbitals around the nucleus there are orbitals in which electrons surround or kind of revolve around the nucleus in a certain direction, in a certain velocity. So let's say this velocity is v of the electron that is revolving around the nucleus, and there is only a single orbit and a single electron because this is hydrogen atom. For other atoms where the atomic number is higher, there you can find many other electrons, and that makes basically the picture more complicated, many more orbits. So we do not want that. So we just want a simplified picture to explain this property. Now as I am saying that this electron on the outer orbit has a charge, electric charge of minus E, alright, and let's assume that this electron has a mass of m. Now you know that electrons have some finite mass that is properly defined. You can check the exact mass value of it, but it do have some finite mass. We define the mass, we symbolize it by m, and also it is given that it is rotating around the nucleus in this orbit with a velocity of v. Now you can assume that this is kind of forming a current loop, right? Because you know electron has a charge and the charge is moving with time with some velocity. So whenever there is a moving charge, it produces a current, because otherwise the charge is stationary. So there is a moving charge means the charge is having a motion, and all you have to do to find out the current is that current equal to charge divided by time, right? So it is basically a moving charge which is giving rise to a current in this case, and this is similar to a current loop. Why? Because we have this electron in a particular orbit around the nucleus, rotating around the nucleus, and it is like the current is flowing in a loop boundary, which is basically this orbital, like this. And this is basically because electron is a charge, electron's flow direction is opposite to the current direction conventionally. So you can think of it like a current is flowing through the orbital like a current loop. So as soon as I have mentioned the word current loop, you immediately will know that if there is a current loop, then there must be a magnetic moment. Alright. So if this mu is the magnetic moment, then the magnetic moment value will be the loop current, which is coming because of the electron's motion around the nucleus in this orbit, loop current, into the area of the loop. The area of the loop actually is basically, if it is a circular orbit, so the area of a circle, you know that this is pi r square, where r is the radius of the circular orbit. You can also say this is the atomic radius or Bohr radius for hydrogen atom. Okay, so it is basically the radius of the first orbit around the nucleus for hydrogen atom, called the Bohr radius. It is a particular standard value also. So this is the case that if you have a loop, the loop has a finite area pi r square, and there is a current flowing inside in the loop boundary because the electron is moving around the orbital. So there is a finite magnetic moment that is present, and that is the moment of the electron. So if this is the electron, so it has a moment which we define by, let's say, mu, and this moment is coming because this is kind of equivalent to a current loop around the nucleus. Now also you have to remember that electron has a mass also. Apart from the electric charge, that electron also possesses a mass, and it is also similar to a massive particle that is moving in an orbit with a certain velocity. So this electron has a mass of m moving with a velocity of v. So its linear momentum will be m times v, and as a result it will also have an angular momentum omega, which is nothing but this r cross p or r cross mv, where r is the atomic radius, okay, v is the velocity in which electron is moving, and m is the mass of the electron. So clearly you can think of it like when the electron is actually surrounding or revolving around the nucleus in this orbital, it has two considerations that we have to take care of. One is the electric charge of the electron, which is giving rise to a current similar to a current loop that gives us a magnetic moment. And on the other hand, this electron has a mass m, and when a massive object, like in this case an electron, is moving with a velocity v, it will have a linear momentum, and because it is moving in a circular motion like a kind of a thing, so it will also have a angular momentum, which is given by r cross the linear momentum mv, and so the electron will also have an angular momentum omega. And now these two are kind of interconnected, right? So the electron has a magnetic moment mu, and also it has a angular momentum omega, all because of it is rotating in a circular orbit around the nucleus. So these two are related properties, and there is no contradiction between these two. So these two will be actually directly proportional to each other because these two will have the same direction, same everything. So basically we can think of it like that they are directly related to each other, or the magnetic moment for the electron in hydrogen atom is directly proportional to the orbital angular momentum of the electron, which is in this case omega. And thus if you also define a proportionality constant, this is the universal constant in this case, which is the gyromagnetic ratio. So gyromagnetic ratio is nothing but the ratio of magnetic moment by the angular momentum. So this is the connection that you have to make between a magnetic moment and angular momentum, that they are directly proportional to each other, and the proportionality constant is nothing but the universally known constant known as gyromagnetic ratio. Okay, now okay, so our second question is done. Now let us move on to the third question. Third question tells us or asks us that which of the following represents the correct choice of a vector potential A vector for a constant magnetic field B vector in the y direction. So first try to understand the question. So it is again, this involves some bit of a mathematics, unlike the last two questions which were mainly conceptual, but this involves some mathematics. and you have to basically know a single formula to solve this. So basically you are asked to find out what is the vector potential value A vector, and the information you are provided it with is the information of the magnetic field B vector. What is that information? Just look closely, that you are told that the magnetic field B is in the y direction. That means your magnetic field B vector can be, if the magnitude of the magnetic field is B itself you consider, then B vector is nothing but B times y cap, because it is in the y direction, right? And the question you are asked is that find out what is the vector potential A for this magnetic field present in the situation. Okay, so the single formula that you have to know to solve this is the famous formula that B, the magnetic field, is equal to curl of the vector potential A. So this is the single formula that you have to use to solve this. B equal to curl of A. Now there are four options given. For the possible answers of A, there are four choices given, and you have to check which choice actually satisfies this relation, so that you have to calculate the curl of the vector potential. So you can take each of these options and calculate the curl, and then check and see whether this compares with the actual magnetic field information that you have been given, whether the answer comes as B times y cap or something else. If it matches with B times y cap, then that will be the right choice for A vector, and if it does not, then that will not be a right choice for this magnetic field. So let us first, let's say, try with the first option. Okay, so I am not saying this is the right answer, I am just saying that let us try taking a curl of the first option and see whether it can produce us with the magnetic field that is given in the question. So the A vector is given in this choice as half Bx x cap plus By y cap. So let us go to the blank page once again. This is our question number 3. So the option choice number 1 was A vector equal to half, I think, what was it, Bx x cap, right? Bx x cap plus By y cap. So it is Bx x cap plus By y cap. Now we have to take a curl of the magnetic vector potential. So how to take a curl, I think you know from the basic idea of math physics. You probably already know that. If you don't, then you can check the Google, or there is a book by, I think, Springer, or this they have a vector, or any math physics book you can check out, and you can see what is the like this formula to calculate curl of a vector. So for now I'll just solve it for you. So you have to see x cap, put x cap, y cap and z cap, and then because there is a gradient, so you have to give del del x, del del y, then del del z. And then A vector is a vector which has components along x cap as b times x, component along y cap as b times y, and because there is no contribution with the z cap, so the z component will be 0, we can see. So this will be 0, and this is how you calculate a curl. So now we have to take one by one. So what will be the coefficient with x cap is basically take cross. So del del y of 0, del 0 del y, minus del del z of by, del del z of b times y. Similarly, for y cap again take a cross, del del z of b times x, minus del del x of 0. Bracket over. Then for z cap you have del del x of this again cross, del del x of b times y, minus del del y of b times x. Okay. So now del 0 del y is 0, because this is a 0. So what will be any derivative you take, it will give us a 0. Similarly, del del x of 0 will also be 0. Now let us look at the other terms. Here this B is a constant, right? So this magnitude of the field, magnetic field is a constant. B is a constant, it does not depend on x, y or z. And here there is a only other term present as y, and the derivative is with respect to z. So they are independent variables, so they have no dependency on each other. That's why this derivative will give you 0. Similarly, for this y cap coefficient, what will we find out is that B is constant, so it will not be affected by the derivative, and del x, del z, x and z are independent individual variables, so that will also give a 0 from the derivative. And then for z cap, you have del x of B times y. Again, there is no same variables present, so B is a constant and y is a separate independent variable than x, so this will be 0. And then similarly, del y of Bx will also be 0 for a similar reason. So all in all, what we get is that the total answer is 0 for the field, because this is the curl of the magnetic field, right? So that will give you the B vector. So curl of A vector equal to B vector, which is nothing but 0. That is seen from this answer. So now in the question you are asked that you have a finite magnetic field present, which has a magnitude of B and which is in the direction of y cap. So you have to get an answer where B vector equal to B times y cap, but in the first option of choice of A vector, you are seeing that the curl of the magnetic vector potential gives you a magnetic field B of 0, which is not the case. So very naturally, the first choice for given in the question, choice number A, will not be the right choice for this question, because it does not match this value of the field. Now we can check for the each choice by yourself. So I'll leave the calculation to you. I'll not show all the other options. I'll only tell you the answer, which is option number 3 probably, and we will just solve that part and show you that actually from this vector potential you will receive a B vector, which is nothing but B times y cap. So let us check this A. A is here, B z x cap minus B x z cap. So remember that what is our A vector choice for choice number C is that half of B times z x cap minus B times x z cap. Let us verify once again so that it will not make a mistake. Bz x cap minus bx z cap. Okay. Now let us calculate the curl. Again the same method, curl of A. Okay, so there will be half factor in front of it because there is a half in A vector. Everything else is the same. X cap, y cap, z cap, del x, del y, and del z. Then you have B times z, because this is with x cap, so B times z is basically the x component of A, which is here bz. Now you have nothing with y cap, so the y component of A will be 0 as seen from here, and you have bx z cap with a minus sign. So the z component of the vector potential is minus of bx. Now calculate it. So this is x cap. Now take the cross, del y of minus bx. Okay. Minus del z of 0. So it is automatically 0. You have seen from the earlier question. Plus it is y cap's turn. So y cap, it is del z of bz, b times z, minus del x of minus bx. Plus for z cap it is del x of 0 minus del y of bz. So you can see from here that del z of 0 is automatically 0 and del x of 0 is also 0. Similarly, b times x has nothing to be taken a derivative with respect to y, so that's why it will also be 0. Similarly, here b times z has no dependence on y, so del y of b times z will also be 0. Only term that you are left with which will be non-zero is this part, this y cap's coefficient. Why? Because even if b is a constant, here there is a variable z present, whereas the derivative is also with respect to z, so it will be non-zero. And for del x, there is a variable present as x, so it is also it will also give you a non-zero derivative. So let us calculate what will be the value. Half y cap, b is a constant, so it comes outside. Del z of del z is 1, minus this minus and this minus makes it plus. B is a constant, so comes outside, and del x by del x is 1 again. So it is nothing but 2b by 2 y cap, which is just b times y cap. So from here it is clear that you have obtained the exact magnetic field that you are asked in the question, that if you have a magnetic field like this in the y direction, b times y cap, then the magnetic vector potential, by taking a curl of which you reach this magnetic field, so you have to get a back calculation for getting the answer. So in this case your answer option is option number C, which is nothing but this result, half bz x cap minus bx z cap. Okay, so this is your answer. So the single formula and the most important rule we have to follow for this question was b equal to curl of a. Okay, done. So then we will move on to the question number 4. So it says that the magnetic field strength in a piece of metal with magnetic susceptibility that has some value minus 0.75 into 10 to the power minus 5 is 10 to the power 6 ampere per meter. So the magnetic field strength means you are given the value of H. H is the magnetic field strength, and you have to calculate the flux density, which is nothing but the B vector, where you are given with the mu naught value, which is the free space permeability, magnetic permeability, and the magnetic susceptibility value, which is chi of the material, is given as minus 0.75 10 to the power minus 5. Now look at one thing carefully. These are small things that you should notice as concepts for in these questions. First thing is that here the magnetic susceptibility chi is negative. So you have already studied probably in your earlier lectures or some other courses that always when there is a diamagnetic property, then the chi becomes negative. So chi is negative means the material is that we are given or we are provided with in the question is basically a diamagnetic material. And you can see what is the order of the susceptibility, 10 to the power minus 5 in this case. And so you are given with chi provided, and then you have been provided H. H is basically 10 to the power 6 ampere per meter, magnetic field strength. And the B, often people confuse B and H, they are true identity, but make it very clear within your head that they both are different quantities. They have different dimensions and different definitions. Where H is the direct magnetic field strength, B is not the magnetic field strength, but it is the magnetic flux density, or I think it is called the magnetic flux density, or I think magnetic induction value, I think. So basically you can call B vector as a magnetic flux density, which is nothing but related to H by this formula, that B equal to mu naught into H plus M, where mu naught is the free space magnetic permeability, H is the field strength, magnetic field strength, and M vector is the magnetization. Magnetization is what? Magnetization is magnetic moment per unit volume of the material. So basically you are asked that what is the value of this B when you have we are provided with the value of mu naught, that is here, the value of H, which is this thing, 10 to the power 6, 10 to the power 6, this thing is the value of H, and the value of chi. Now how to involve chi in this relation? So you know that magnetization is related to the magnetic moment by this formula, that M equal to chi times H, where magnetization is directly proportional to the magnetic field strength H, and the proportionality constant is known as the magnetic susceptibility, or chi. So in this case, if you go on further, you will see that just put the value of m in here. So it is mu naught into h plus replace m by chi times h. So what you are left with is that mu naught into 1 plus chi. Just take a common and then h vector. So basically what we are suggesting is that your b equal to not only mu naught h vector plus m vector, but if you replace m in terms of h, because m is anyway chi times h, then you get the whole formula in terms of only the magnetic susceptibility, which is chi, free space permeability, which is mu naught, and the magnetic field strength or h. So here b equal to mu naught into 1 plus chi h vector. Now we have to calculate the b vector value. So all the other values we are already given, we have already been provided with in the question. So we'll just put in the value, plug in the value and check what is the correct option. So just put in the value of mu naught, chi and h from the question. Which are those? So basically mu naught is given here is 4 pi into 10 to the power minus 7 Henry per meter. That means it is an SI unit. And then 1 plus chi is also minus, so minus 0.75 10 to the power minus 5 means e minus 5, and then h vector is nothing but 10 to the power 6 ampere per meter. So all of these are in the SI unit. Now let us calculate what is the value coming as. So 1 plus chi, so 1 plus chi is given as basically it is a minus sign because chi is negative. So 1 minus 0.75 into 10 to the power of minus 5. Just use your calculator. So this I am using my calculator. So I am getting some value of 0.9999 something from this this part. So now it has to be multiplied with 4 pi into 10 to the power minus 7 and then 10 to the power 6. So into 4 pi to 10 to the power minus 7 into 10 to the power 6. So I have calculated it using my calculator. It is showing a value of 1.26 or 256, 1.256 Tesla. So this tells you that your option number 1 is correct because it has a similar value, that the flux density is 1.256 Tesla. Okay. Now let us look at the next question. So just read the next question carefully. This is again a conceptual question, and this question is directly answered, and even this theorem has been proven in the lecture itself. So probably you know the answer. So it is said that according to Bohr-Van Leeuwen theorem, the magnetic susceptibility in a classical system is what? The question's options are positive, negative, 0 and unity. So just I hope you know the answer. So if you know the answer, you can tell me the answer or I will let you know. Okay. So just think of what will be the answer for this question. Okay, so basically I'll give you the answer, that this Bohr-Van Leeuwen theorem says or proves that the magnetic susceptibility for a classical system is always 0. Now this is a very important theorem and it is already proved in the lecture materials, but again I'll explain it here for you that why it is 0. And still if you have any doubt on the proof, you can tell me. You can ask me in the tutorial. So this is question number 5. The Bohr-Van Leeuwen theorem or BVL theorem in short says that for any classical system in thermal equilibrium, with the surroundings, the magnetization equal to 0. So let us prove this. So basically, let's say you have n number of charged particles present in a system, each having their positions defined as R1, R2, Rn, which is given by this index I, where I value varies from 1 to n. Similarly, these particles, these charged particles have a finite momentum which is given by Pi, which is nothing but P1, P2 up to Pn. Okay. So now, if this is the case, then what will be the energy of such a system of n charged particles? So the energy E as a function of R dot P for all the particles. So we use the index. So this is the energy correspond to the energy for the n particle system. Now you have to calculate the partition function for this case. Okay. So this is the classical idea of partition function for such a system. This is an idea of StatMech you probably are familiar with. So I'll not go into the details. So the partition function Z is nothing but given as some sum over E to the power minus E by kBt. Where if E is quantized as En, then this indexing sum will be, the sum will be all over the n value of the quantization. Okay. So this is just to the power of minus En by kBt. Okay. Now, because this is the continuous system, because there are n number of particles where n can go to infinity, so this is a continuous system of particles. So instead of discrete summation, we'll have to use integration, because continuous summation is done by integration only, we know that. So for a continuous system of particles, total partition function Z equal to integral over e to the power of minus Re, Ri, Pi by kBt, then dr1, dr2 up to drn, and also the momentum coordinates, that is dp1, dp2 dot 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 dpn. Now here I am not putting too many integrals, but you have to understand that all of this dr1, dr2 has an individual integral sign, and all these integrals go from minus infinity to plus infinity, like for even for position and for momentum. So they can choose any value from minus to plus infinity. So this is just, let's say we put the integral to totally in a single place. So we use the dot 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 because there are many number of integrals, so we just merge them together by this dot 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 sign. So this is minus infinity to plus infinity, all the integrals e to the power of minus e as a function of position and momentum by kBt into d to the power of 3n r vector, and this is d to the power of 3n p vector. D to the power 3n r vector, because this is a dq bar type of a thing, because this is a, if r is a this is a three-dimensional space and a vector, then this will be dq bar, and because there are n number of particles, that's why d to the power 3n r. Now what will be the case is that okay, so in presence of a magnetic field, so in the momentum value changes. So the momentum value changes to P equal to small p, the changed momentum value, equal to capital P plus Q times A, where A is a vector potential, P is the mechanical momentum value, which can also be the canonical momentum if there is no vector potential part A vector, but there this q is charge and A vector is a vector potential. So then in presence of a field, magnetic field, the canonical momentum will change by this factor of qa. So this small p is canonical momentum, so this changes. So now the mechanical momentum p vector new value will be the new canonical momentum small p minus qa. Okay, so this is the case if q is the charge of each of the charged objects. So then this is the mechanical momentum, and so you know that the kinetic energy is nothing but the mechanical momentum whole square by twice m. So this will be 1 by twice m p vector minus q a vector whole square. So this will be the integral will be minus infinity to plus infinity dot 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 minus infinity to plus infinity. And then because this energy means nothing but the kinetic energy plus potential energy, and in any case if there are no other interaction term etc mentioned, so then the potential energy will be negligible or zero. So then the only kind of energy the particle system will have is the kinetic energy. So this kinetic energy e to the power minus e by kt is basically e to the power of minus 1 by kt of p minus q vector whole square. Again the similar d cube 3n r vector and d cube 3n p vector. Okay, so now you see that here there in the integral there is d cube p or dp vector, but in the actual integrand it is p minus qa. So the shift in the momentum that can be easily adjusted because the integral limit is from minus infinity to plus infinity. So the shift can be adjusted very smoothly, and by absorbing the extra a part in p minus qa, so absorbing the extra a part in the Hamiltonian or in the energy, by the shift of the momentum origin from minus infinity to plus infinity. So because the integral limit is from minus to plus infinity, so you can easily shift the momentum origin as you can choose, and that's why you can easily absorb the extra term that contains a vector potential a vector, and again you are left with the same term. So for example, you can choose this p minus qa, that this total quantity, as a new quantity of p prime. So then it will be just like e to the power of minus beta, where beta equal to 1 by kbt, to the power minus beta p prime whole square, and then d cube r vector, all the r vectors are on, and then d cube 3n r vector, and then d cube 3n p vector. So d cube 3n p prime vector, because if you take a derivative, so it will be dp minus 0 equal to dp prime. So if that is the case, then you can see our total partition function z does not depend on the magnetic field b vector or the field strength h vector, because it is not related to even the magnetic vector potential a vector. So if a is itself not present, so then how can b vector can be present? So basically our classical partition function for this kind of a case is independent of the vector potential a vector or the magnetic field b vector. So then if that is the case, then you know that the Helmholtz free energy equal to minus kbt ln z. So if z is independent of any magnetic field, then of course the Helmholtz free energy will also be independent of any field. So this is basically Helmholtz free energy. And we know that, one second, yeah, and we know what is the definition of magnetization. M is basically nothing but minus del F del H. So, or you can also say that it is minus 1 by volume del F by del B. So either by magnetic field strength or by the magnetic flux density. And because F is independent of both B and H, because the partition function itself does not depend on B or H, so F is also independent of B or H. So then del F del V will be 0. So the magnetization will be 0. So this what was that? Bohr BVL theory, basically this BVL theory tells you, and it is also proven from the theory assumptions, that by classical idea, if you go for a classical object, the magnetization will always come as 0. But in reality, you will see that there are always objects, there can always be objects, solid objects, where there is some finite magnetization present. It is not always 0 magnetization. So that basically contradicts this theory. So from there, the basic notion comes that magnetization or magnetism is not a classical phenomena. It is something that can only be explained in a system by quantum ideas. So basically it tells you that BVL theorem tells us that magnetism is not a classical phenomena. It can only be explained by quantum ideas. That is why even if you have in reality you have solid objects, they have a finite magnetization M not equal to 0, but those are not treated classically. Okay, so in real objects it can have M not equal to 0. Okay, so this question is also done. Now let us take question number 6. Now this is again a very conceptual question. It asks that a solid is composed of ions with all their electronic shells filled. Then which kind of magnetism is relevant here? Okay, so again read the question, that there is a solid and they are asking that the solid has ions with all the electronic shells filled. That means there is no unpaired electron in any of the shell present. All the electrons are paired up. Like say, if let's say you have a shell like this. Let's say if you have a P shell, you know P shell there are 3 parts. So this part, this part, this part. So this is the P shell, Px, Py, Pz. And the solid is such that all the shells are filled with electrons, completely filled. That means here there are pair of electrons, here there are pair of electrons, then again pair of electrons. So there is no unpaired electron present. So then what kind of magnetism is relevant here? Of course, the answer is very simple, that the magnetism, only kind of magnetism possible here is diamagnetism. Because diamagnetism does not depend on unpaired or uncompensated electron movement. Unpaired electron movement. It is something that is inherently present in all the objects. Diamagnetism is something that is common in all the objects. It is present always in every object, because it does not depend on the whether the material or solid has some unpaired electron or not. Unlike paramagnetism, because in paramagnetism you need to have at least one unpaired electron present in the system. Otherwise, you cannot have paramagnetism. So all these derivations are already done in the lecture. So there is a basic relation that tells you that how the parametric contribution looks like or how the diametric contribution looks like, and from there you can see that the diametric contribution does not need any moment component or any uncompensated or unpaired electron moment. So that is why when there are no other kind of effect that can be present in the system, like there can be no paramagnetism effect right now, so then the natural magnetism that is inherently present in the system will become the most effective thing, which is the diametric property, because this diametric response is very weak inherently in a system, so it is often suppressed by the other responses of the system. Like say, even if every other material has some diametric property, but you cannot see or feel the diametric property until and unless there are all the other effects are absent from the system. Like say, if the material is absolutely not paramagnetic, that means there is no unpaired electron present in the system, then paramagnetism cannot occur, and that is why paramagnetism strength cannot suppress over the diamagnetism strength, and then you can feel that there is some diametric property that you can associate and feel for the system. So there is a formula that is derived. I will not derive that, I will just write down the formula which one I am talking about. So I think this is for question number 6, I think. Question number 6. So the formula I am telling you about the magnetic contributions is basically, let me just check and write down so that I do not miss out any of the terms. Okay. So basically, if you look at the Hamiltonian of the system, then it will be, you can follow the lecture notes for the detailed discussion or derivation, but it can have a formula like this: L plus Gs vector, where mu v is the Bohr magneton, which is the standard unit of magnetic moment. T naught is the most conventional contribution to the Hamiltonian, which is the basic kinetic energy contribution. That is nothing but this whole I pi square by 2I7, where pi is the canonical momentum, and this mu b is the Bohr magneton, L vector is the orbital angular momentum, S vector is the spin angular momentum, G is the Landé G factor for the system, plus, so this is basically derived by perturbation theory approach. So you can check the derivation and do the derivation by yourself from the lecture itself. So this is psi square plus yi square. Okay, so this is the term. So now this first term is the conventional term of kinetic energy conventional in the Hamiltonian. The second and the third term are extra, okay, because they involve the magnetic field. You can see that here the third term has a magnetic field B, and the second term has all these Bohr magneton. Sorry, I missed out another magnetic field factor B vector here. So this is this dot product of B vector. So this whole term is giving us the paramagnetic contribution in the system, and the third term will be giving us the diamagnetic contribution in the system. So you can see that both the terms have this B vector present. That means they can only appear when there is a field that is applied in the system. Okay, so they are dependent on the field. But one major factor that you will notice is that in this paramagnetic contribution term, you have these terms like L vector and S vector, which is the orbital angular momentum and the spin angular momentum. But if there are no unpaired electron present in the cells, that means even if you have a S cell, which is a single compartment, and then if you have a P cell, which is like 3 compartments, all of them have totally filled position of electrons, like paired up. So there is no unpaired electron. So then there is no individual moment that is present. So in this case, in such a case, if this is the thing, then you know that for S orbital, the L value is 0 for each of the electron. For P orbital, the L value is 1 for each of the electrons. And For each one of them, you will see that this ml values will be different. So here ml equal to -1, ml equal to 0, and ml equal to +1 for each of the compartments. And for S, L equal to 0, so ml has a fixed value of 0, because ml is the z component of the orbital angular momentum L. So ml value varies from -L to +L. So for L equal to 0 in S orbital, ml equal to simply 0. But for L equal to 1 for P orbital, ml can be -1, 0 and +1 according to this formula. So that's why the three compartment comes, and all of these three compartments, if you look at this, you will see that the total L is nothing but the sum over all the L values, right? So like for the first case, it is S orbital, so anyway L equal to nothing but 0. For the second case, it is p orbital. So in a general way, L equal to 1. But then you have paired up electrons in each of the shells. So in each of the shells, you have this -1 plus 0 plus 1. The summation of all of that will give you again a 0. So the total orbital angular momentum is coming at 0. And similarly, the net spin angular momentum will also be 0, because there is no uncompensated or unpaired spin that is present here. In each of the compartments, you have a up spin and then the corresponding down spin. That means even if it has a plus up spin and this has a minus up spin, both of them sitting together cancels out each other and give you a net spin angular momentum as 0. So that is why this total contribution, this total second term is totally 0, because this is 0 and this is 0. So this whole term will be 0. So whenever there is no unpaired electron present in the system, the second term vanishes. That means there is no paramagnetism present in the system. And then what comes relevant is the third term, which is the weakest term, weakest contribution. So this is the first one, that is T naught, it is the most dominant contribution to the energy or the Hamiltonian, because this is the conventional kinetic energy term. The second term, which is paramagnetic, it is still weak but stronger than third term. So compared to the diamagnetic contribution term, the second term is still having a finite strength. So if you have an unpaired electron, then this L and S will be non-zero, and then this will have a non-zero value, giving rise to paramagnetism in the system. But if you have none of these, that means L equal to 0 and S equal to 0, then you directly come to this third term, which is dependent on the field B by this B square x square plus y square, and this is your diamagnetic contribution. So you can see that it does not depend on any L or S. So this is, even if these are 0, but these are not involved in the third term, which is the diamagnetic term. So that is why even if in the system you have no uncompensated or unpaired electron spin present, you do not have to worry about getting diamagnetism, because diamagnetism is inherently present in the system whenever there is a magnetic field. So this is what tells you the answer, that in such a case, when there is no unpaired electron or present, or all the shells are fully occupied with electrons, then the only option is that the only magnetism that can be effective other than the conventional one is the diamagnetic property, which is basically a negative magnetism, because in this case the magnetic moments align anti-parallel direction to the field, and it is a very weak magnetism that is not mostly observed in most of the materials because it is so weak in energy. But anyway, the answer is diamagnetism. Now for question number 7, again a conceptual question. It says that magnetic susceptibility of a diamagnetic material is, the options are positive, negative, 0 and infinity. As I was telling you that the diamagnetic material is something that repels a magnetic field. So we know that the magnetic susceptibility chi is such that m equal to chi times h, right? Where m is the magnetization, which is the magnetic moment per unit volume. Chi is the magnetic susceptibility, and h is the external magnetic field strength. So we know this is a convention that is very well known, that chi is negative for diamagnetic materials, chi is positive for paramagnetic materials. But of course there is some value limit also, so you cannot just put the sign and everything. There is also a value limit that so your chi So I'll just write down here at the side of it. So question number 7. We'll know probably the difference between all three very clearly, but again for the sake of it, let me write it down. So this is diamagnetic property, this is paramagnetic property, and this is ferromagnetic property. So diamagnetic property is when the material, the solid that you are provided with, has no unpaired moment or magnetic moment present inside. When you apply a field, then it has some very weak magnetization that is induced inside it, but otherwise it do not have a magnetization. So it is the weak dimagnetization. And then paramagnetic materials are which those have a already unpaired electron spin that is present inside the system, inside the electron shells, and that is why you have magnetic moment. But when you do not apply a field, they all are randomly oriented and cancelling out each other, and you do not see a finite magnetization. But when you apply a magnetic field, all of these moments tend to align towards the magnetic field direction, and that give you a finite non-zero magnetic moment or magnetization value. Then comes ferromagnetism, which are materials where the magnetic moments are already aligned in a particular direction, like it has already magnetic domains, but if those direction has even without field, you have a particularly aligned direction of magnetic moments. But when you apply a field, all those moments again try to shift from their original orientation, and all of them combinedly align towards the magnetic field direction. So that is how ferromagnetism is defined. Now, as far as the value of susceptibility is concerned, it is always very well known that diamagnetism had negative susceptibility and para and ferro has positive susceptibility. But what will be the value? It is that for diamagnetism, the value of chi is from -1 to 0. So anything that is negative, that is less than 0, and the maximum value can be -1. So for ideal perfect diamagnet, chi value will be the maximum -1. It cannot go beyond this in the negative side, and the highest value it can achieve is any value that is negative and or less than 0. Okay, so chi equal to -1 for superconductors. Later on, when in this course we'll learn about superconductors, then we'll see that for superconductor is a perfect diamagnet. There the diamagnetic susceptibility value chi equal to -1, like a superconductor. And for paramagnetic materials, the chi value is positive, that means it is greater than 0. But again, it is less than some epsilon, where epsilon is a small value. So that means it is a very small, weak, but positive susceptibility. And for ferromagnetism, the chi value is much greater than 1. Strong susceptibility chi. Okay. Based on this, you can also find out what is the approximate range for relative permeability for these cases. Relative permeability is nothing but mu r, which is basically the total permeability divided by the free space permeability, which is nothing but 1 plus chi, because you know that mu is defined as mu naught, the free space permeability, into 1 plus chi. So this is how, if you take the ratio of mu by mu naught, you will be left with mu r, the relative permeability, which is nothing but 1 plus chi. So now for diamagnetic materials, because chi is already negative and maximum negative value it can take is -1. So the maximum value of mu r here will be 0 when chi is -1, and otherwise when chi is negative generally, then it will be less than 1. Okay. So the value will be either less than either equal to or greater than 0. Sorry, it is greater than 0. It is greater than 0, and then either that or less than 1. This is the range. Similarly for paramagnetism, because this is a small positive value, so mu r equal to 1 plus chi. So 1 plus some small positive value will be a positive value, which is again small. So it is basically mu r range is 1 to 1 plus epsilon. Then for ferromagnetism, when chi is much greater than 1, then this mu r equal to 1 plus chi, where chi is much greater than 1, so then mu r will also be very much greater than 1. Okay. And similarly, also there is a range for mu and mu naught relation. So basically if mu1 is less than 1 for diamagnetic case, then mu by mu naught is less than 1 or mu is less than mu naught. That means actual permeability is less than the free space permeability. Similarly, for this case, mu1 mu by mu naught is less than 1 plus epsilon, but it is greater than 1, right? So here basically mu is greater than mu naught. Even if not by very large amount, but actually the net permeability is greater than the free space permeability. And for ferromagnetic substance, for the same reason, mu is much greater than mu naught. Okay, so this free space permeability mu naught is much smaller than the actual permeability. So this is the answer. So that was asked in the question, that magnetic susceptibility of a diamagnetic material is of course negative. If the answer was for paramagnetic material, then you have to choose positive. Okay. Then let us read the next question, which is question number 8. So it talks about the Einstein-Dehaas effect and asks that Einstein-Dehaas effect experimentally proves the relation between which of the option is correct. So this is again the content of lecture 1 from week 1 lectures. You can go and check that out. But the answer, I will tell you, the answer will be option number 3, which is the relation between magnetic dipole and the angular momentum. So basically, as a theoretical idea was that the magnetic dipole moment and angular momentum are related, that they are directly proportional to each other, where mu is proportional to omega, and the proportionality constant is gyromagnetic ratio. But this theory was experimentally came into proof by this Einstein-Dehaas effect, this experiment. So this experiment has been discussed in the lecture itself. It is basically nothing that a ferromagnetic material is suspended from a rod or some hook, whatever. This is a ferromagnetic material, and around that, if there is a around this ferromagnetic material, there is a current loop that is given. There is a loop current that is given connected. So loop current that is given. This is connected to a battery outside. So there is a particular direction that current is flowing through the loop, okay, and coming back. And because current flow produces a magnetic field, so basically this current that is flowing inside the loop in a particular direction will produce a magnetic field inside, and that will magnetize the ferromagnetic material that is kept inside, okay. And on the ferromagnetic material you have an optical mirror placed, which is actually set there to detect the rotation of the ferromagnetic object. So if the ferromagnetic object rotates inside the loop, then this mirror will reflect some light, and that light will be, so some light will come, it will be reflected from the mirror, and it will be detected by a optical detector. So this is for the record of the data. But otherwise you will see that whenever you apply a current in the loop will generate a magnetic field around the material and magnetize the material, and as a result of that the material will start to sorry. So this material will start to rotate inside the loop. So that basically proves the experimental relation that magnetic dipole moment and angular momentum are related to each other. And the basic cause is that whenever you apply a current in the loop, it will produce a magnetic dipole in the material, because the material will be magnetized. And since the magnetic dipole moment mu is proportional to the angular momentum omega with the gyromagnetic ratio as the constant, so as a result of that, initially because there was no angular momentum present, and now suddenly because of the magnetic moment that is induced, Because of that, there is also a finite angular momentum value that is coming into the picture. So you have to preserve the net angular momentum. So by following the conservation of net angular momentum theory, if initially there was zero angular momentum and now you have a finite angular momentum, so to conserve the net angular momentum, now the material has to have a rotation inside the loop, and as a result that rotation will be detected by this optical detector, this mirror reflected light, and that rotation is basically periodically over time it is detected and noted down, observed in the data. And even if you reverse the direction of the current, you will see the field will be induced in the opposite direction, and as a result the angular momentum it will provide will cause the material inside to rotate in the other direction. So this was the first experimental realization of this theoretical idea that was given, that yes, actually the magnetic moment and the angular momentum are related to each other, and that is proven by the experiment when you record the data of the rotation, how much it is rotated, so then what is angular momentum, and record the data over time. So basically you can keep a track of the data with frequency, and from there on you will get the angular momentum value, and etc etc. So this is the answer. Then question number 9 is interesting. This is a very common question that comes in exams. Most of the competitive exams has very this common type of questions based on this idea. So basically you have been given sodium atom. So you know sodium has an atomic number of 11, Na11, and it is said that if the energy levels of sodium are filled in the following sequence, so basically this is the rule, Ohm's rule you have to follow, how the orbitals are getting filled with electrons. So this is 1s, 2s, 2p, 3s, 3p, 4s, 3d. Then the ground state of Na11 is described by the term symbol. Which one of this is true? Okay, so this is a very common question that I was saying, that you will be given an atom which has a particular atomic number, and you know the Ohm's rule, that how the atomic number, the electrons will be arranged in the different orbitals, filling up in the different orbitals, and then based on that you have to guess you have to not guess, you have to detect, you have to tell the ground state of that atom. So I'll tell you the basic idea. So the idea is that, I think this was question number 9. Idea is that whichever atom you are given, so from there you have to first know its atomic number. Okay, so that is the first thing. From the atomic number you have to calculate what is the configuration of the electron filling in the orbitals, like 1s2, 2s2, like this. What is the filling of the orbitals in the atom? So orbital configuration. Then from there on you will get to see what is the spin angular momentum value, that is what is the S value, then what is the L value, orbital angular momentum value, and as a result what is the J value, which is the net angular momentum, that is L plus S vector. Okay, so J equal to L plus S, and if you have to take the modulus value of J, then the value will be from L minus S mod to L plus S. This can be either this or this. So based on, if the orbital is less than half filled, then the J value you have to choose as L minus S. But if the orbital is more than half filled of its capacity, then it will be chosen as L plus S. So it is for less than half filled orbital, J is L minus S mod, and for more than half filled orbital, it will be L plus S as the J value. Also, the ground state will be written as these different values, like it can be S, capital P, capital D, or capital F. So how are those defined? So basically, if your electron is for L equal to 0, then it is L. So if it is L equal to 0, then it is S. If it is L equal to 1, then it is P. For L equal to 2, it is D, and L equal to 3, it is F. But remember that these are not small letters. These will be in capital letters because that is a symbolization of the ground state. So let's say if you're in your case, if you're it is for L equal to 0, then it will have to put capital S here. Then in the superscript you have to write in the left 2 small s plus 1. Here small s is the spin angular momentum. Do not confuse it with this capital S, because this capital S identifies a ground state when L equal to 0. And for the subscript on the right, you will have J. J, the mod value of J. I mean, it can be mod of L minus S or it can be L plus S, depending on whether the orbital is less than half filled or more than half filled. So based on that, it can also take values like 2s plus 1 pj or 2s plus 1 dj or even f, depending on whether L equal to 0 or L equal to 1 or L equal to 2. Now let us check for sodium's case. So sodium is Z equal to 11. As I said that first you have to know the atomic number. Now we have to check the orbital configuration of the filling of the electron. So 11 means it is 1s2, 2s2, 2p6. So calculate that it is already 6 plus 2 plus 2, that means 6 plus 4, that is 10. So 1 electron is left because the total atomic number is 11. So 2s2, 2p6, 3s1. Okay, so this is the Hund's rule that you have to follow. You cannot just put any orbital anywhere. There is a particular sequence, and also this S orbital has a maximum capacity of 2 because S has a single compartment. So maximum 2 electrons can sit here. Maximum electron capacity is 2. Similarly for P, there are 3 compartments that are present for Px, Py and Pz. So here in each of the compartments maximum capacity is 2, right? So there you can get 2 plus 2 plus 2, that means maximum capacity of electrons for the p orbital to be fully occupied is 6. Okay, so similarly for D also you have 5 compartments, and for it to be fully occupied you have to take 5 into 2, 10 electrons. So this kind of things will occur. But for now let us focus that let us write down the sodiums. So this is just a generic case, I was just trying to make you understand, but for sodium let us write down the exact atomic configuration of the orbitals. So it is 1s2, 2s2, 2p6 first. So 1s2, this is, let's say 1s2. So there are s orbital with 2 electrons. Then 2s2. So this is again an s orbital with 2 electrons. Then 2p6. So there is a p orbital with 3 components. Each component have 2 electrons fully occupied. So this is 2p6. 2 into 3 compartments, 2p6. Okay. And lastly there is 3s1. So this is 3s1. So there is only a single electron in this s orbital, that means 1. So you can see easily that you know that for all the electron shells which are fully occupied with electrons will have a 0 contribution in the orbital angular momentum L value or in the spin angular momentum S value. So up to all these 2p6 they are fully occupied by electrons, right? So they will have 0 contribution in L and 0 contribution in S. But this last one has a unpaired electron. So this compartment has unpaired electron. So only this compartment will give rise to a non-zero value of L and S. Now this is very easy to guess that because this is a single electron sitting in a s orbital, so s orbital will have small l equal to 0. That means it is a, for it, because there is a single electron, so the only value of L possible is 0 because this is sitting in a s orbital. So the capital L value will also be 0, which is the orbital angular momentum. So now for the spin angular momentum, because there is a single electron that is sitting here, right? So electron spin can be plus half, because there is a single electron spin. We consider that this is the half spin, so this, let us take it as plus half. Now what is the J value? So I told you that if the orbital is more than half occupied, then L plus S, and if it is less than half occupied, then L minus S. But for this case it is exactly half occupied, not less than half, not more than half, because S has maximum capacity of 2 electrons and there is 1 electron. So this is exactly half filled. So in this case you do not have to think much, you just have to know that whether you choose mod of L minus S, the answer will be half. or if you choose just directly L plus S, the answer will be half. So this is the same value, so there is no confusion. So J value is half. And what is 2s plus 1? 2s plus 1 is basically 2 into half plus 1, which is 2. Okay. And also the unpaired electron is sitting in the L equal to 0 orbital. So that means the ground state will be, for L equal to 0, is capital S. And the superscript is 2s plus 1, which is nothing but 2 in this case. And the subscript is J, which is nothing but half in this case. So for sodium atom, this is the ground state, that's 2 is half. Let us check whether that option is given. Yes, so this option is given in option number 4. So we'll take it option number 4. And then the last question is, the magnetic moment of an electron in the 2s orbital according to Bohr's theory would be, the value is given in units of Bohr magneton, which is the standard unit of magnetic moment, which has a value of EH cut by twice m. Now just look at the question carefully, that you are asked that the electron is sitting in the 2s orbital. So 2s means here the n value, the principal quantum number of this orbital is n equal to 2, right? But this is again a s orbital. So for s orbital we know that small l value is 0. The orbital magnetic moment has a quantum number corresponding to it, and the orbital quantum number value is 0, L equal to 0 for s orbital. Now you have to follow Bohr's theory. Bohr's theory, what is Bohr's theory for orbitals? So Bohr's theory tells you that momentum mvr equal to nh cut. That means if there is an atom which is where an electron is orbiting around the nucleus with a orbital radius of r with a velocity of v, and that electron has a mass of m, then the angular momentum mvr value will be quantized in units of h cut, and the quantum number n can take values from 1, 2, 3, etc. all the positive integers. So here n is the principal quantum number, and basically this is how we can quantize the orbital momentum or orbital angular momentum. Quantized angular moment. So this is the Bohr's theory. Now you are asked to calculate the magnetic moment for the electron. So we will use the basic idea or basic definition of magnetic moment, not very complex, is that magnetic moment equal to loop current into loop area. So if the electron is in the 2s orbital, let's say this is the nucleus here somewhere, and this is the 2s orbital around the nucleus, and the electron is revolving around the nucleus in this 2s orbital. So for here n equal to 2 and your L equal to 0. This is the electron, and this is the mass of the electron. This is the orbital radius of this 2s orbital is r. Okay, and this is the center point or the nucleus. So because the loop radius is r, so the area of the loop equal to simply the circular area is pi r square, right? And the loop current is nothing but the electronic charge E divided by the time period of the electron to rotate around the orbital in a circular motion. So E by tau, let us say that tau is the time period of revolution of electron in the loop. So tau, time period. So time period means this is basically the loop circumference 2 pi r divided by v, the velocity of the electron. So tau equal to 2 pi r by v. Now we can put in this value here. The loop area is pi r square. Again put in the tau value. So this is tau equal to 2 pi r by v into pi r square. So this is basically EV by 2 pi r into pi r square. So pi and pi cancels out. This is basically EVR by 2. Okay. So but you have to again further simplify it, because you have to put it in the units of mu b. Mu b is the Bohr magneton, which is basically EH cut by twice m. Now if it is EVR by 2, let us try to put it in that form. First of all, let us say this is E by 2 into mvr, because you have to multiply a m in the denominator, so you have to also multiply a m in the numerator. Okay, so that both of them cancels out each other. Okay, so this is basically E by twice m into mvr. Now mvr, you know that mvr from following the Bohr's theory of orbitals is that the mvr momentum is nothing but nh cut, where n is the quantization number that can take all the positive integers values from 1 to etc. Okay, so mvr equal to replaced by nh cut. Now this is nothing but eh cut by twice m into n. So eh cut by twice m is basically the standard value of Bohr magnet and mu b. So this is basically mu b times n. So the magnetic moment for that electron in 2s orbital is basically n times mu b. Now n value, you know that n is nothing but the principal quantum number, and for 2s orbital n equal to 2, I already mentioned. So you have to choose that your magnetic moment for this electron is nothing but 2 times mu, because you have to put in or plug in n equal to 2. So this is the right answer, that your, let's check this value. So it is plus 2 mu b. Okay, so this is where the 10 questions end. Now for your convenience, I have just put in a chart that is already mentioned in the lecture PDF. So this will help you to understand the calculation of the ground states by using this rule, like this question that was followed earlier for the sodium atom in question number 9. So similarly, you can practice to check yourself whether you can actually calculate for any kind of problem you are given with to exactly calculate the ground state. So you can check with this chart and check the calculation by yourself. Let me solve one for you so that you get the idea. So let me take this number 3. Okay, so number 3 is basically a D shell. D shell means L equal to 2. Okay, so D shell means L equal to, so you know D shell has 5 compartments. So 1, 2, 3, 4, 5. So D shell L equal to 2. So you know if L equal to 2, then ML can take values from minus L to plus L in intervals of 1. That means it can take values of -2, -1, 0, +1 and +2. So all these values give rise to a single compartment, and that's why you get 5 compartments for 5 values of ml. Now in each of the compartments, the structure is given that you have a single electron in first 3 compartments and the last 2 compartments are totally empty. So spin down electron in the first 3 compartments and these 2 are empty. Now you have to say what is the ground state for such a configuration. Okay, so first of all, I told you that for calculating the ground state, you have to know the S value and L value so that you can calculate the J value. Okay, first of all, there is already 3 unpaired electrons that are clearly seen in this case. So S value is easy. Half for each of these electrons. Now you know that for electron, this is by default fixed that for an unpaired electron, S value will always be only half. And ms value, which is the z component of this orbital spin momentum S. So the z component eigenvalue of the spin angular momentum is ms, that can take values of plus minus s, which means that ms can take plus minus half values, but s value is fixed for electron as half for a single electron. So there are 3 unpaired electrons, so that half for each of them. So half into 3, that means S equal to 3 by 2. So let us check whether we have correctly calculated or not. So this thing, as you can see, S equal to 3 by 2. So we are correct. Now we have to calculate the L. So the formula of L is written here, that capital L you have to calculate by taking off the sum of all the small l values, small lz values, right? Small lz means basically the ml values. So your capital L is basically the sum of all the compartments and electrons of the small ml values. And ml values are these values, -2, -1, 0, +1, +2, depending on in which of the orbitals, which of the compartment electrons are occupying in. Okay, so there are 3 electrons with -2, -1 and 0. So let us take the summation. Each of for each electron, this for one electron is -2, then -1 plus 0. So this is basically -3. Okay, so you can take a mod value because L cannot be negative, right? The capital L value cannot be negative, so you have to take a minus, absorb that minus inside the modulus, and that L value is just 3. So this is your L value, which is coming as 3. It is again matched with our calculation. Then you have to calculate J. Okay, J is nothing but J vector equal to L vector plus S vector, the net momentum, net angular momentum. Now there is this rule that I had mentioned, that if the orbital is more than half filled, then it is L plus S, the value of J, and if it is less than half filled, then it is just mod of L minus S, right? For this case, you will see that there are only 3 electrons in this case, only 3 electrons. That means for d orbital, you know that there can be maximum 10 electron capacity for d orbital. So that means half of 10 electron is 5. So half capacity or half field means 5 electrons in d orbital. But here we have 3 electrons. We have only 3 electrons. That means it is not half filled, it is less than half filled. So this d orbital is less than half filled because it has 3 electrons. And that is why you have to choose the rule of mod of J, that is equal to simply J will be mod of L vector minus S vector. So if your L is 3 and your S is just what you calculated is 3 by 2, right? So 3 minus 3 by 2 is 6 minus 3 by 2. It is just 3 by 2. Okay, so your J is coming as 3 by 2. So now it is time to write the ground state. So your ground state, because you are already in the uncompensated spins are already in the d orbital. So d orbital has, you know that L equal to 2, and as a result the ground state will always also be capital D, because in ground state you have to write it in the block letter. So it is capital D and then 2s plus 1, and bottom it is just J. So just put in the values, because S equal to 3 by 2. So 2s plus 1 is 3 by 2 into 2 plus 1 is 3 plus 1, which is 4. So above it is 4, and for J value it is 3 by 2. So let us check whether we have done it right or not. So it is what is the thing? Okay, sorry, I have made a mistake, that here it is mentioned that the ground state is not D but F. So how is that coming? Okay, sorry, I made a mistake, sorry, my fault. Because you know that the capital L value where it is coming as 3, so we completely ignored that. So you have to take the capital L value for your convention of the ground state. So because by the summation of ml, your capital L value is coming as 3, and you know that capital L comes as 3 only for F orbital, because S capital L is 0, P capital L is 1, D capital L is 2, and for F capital L is 3. So because from the calculation we did it right, that capital L is actually coming as 3, but while considering it we confused the value with small l. So it is not the value of small l we have to consider, it is the value of capital L. So that is why, because the capital L is 3, so you have to take F as the ground state. Otherwise the calculation is just right. You can check with the chart that it is just F 4 3 by 2. This is the ground state for this case. Now similarly, there is a whole chart present for all the possible configurations that can be given there. You can just pick out any of them by yourself and just do the calculation by yourself, and then check and compare whether you are doing it correct or not. So this will be a good practice for you. And so we are finished up with all the important questions. So let us finish the tutorial here only, and in the next tutorial I will be solving for you the actual week 1 assignment which is given to you for the week 1 submission. That will solve in the next week's tutorial, that is the next Tuesday, same time 7 to 9. Okay.